Welcome, this is lecture number 33. In this lecture, we are going to talk about loop gain analysis and understanding model limit using MATLAB. So, in this talk, we are going to first construct the small signal closed loop block diagram. Then we need to understand the loop gain and its design requirement. Then we need to validate closed loop small signal model using MATLAB transient simulation. And here I am taking a PID controller case study and try to identify the model limits. Okay. So, this today presentation mainly in the previous I think lecture number 30 we have shown detailed process how to validate small signal model, and that was for open loop converter. So, we want to take that as the reference class for this today class, so that we can some of the step we can just skip because that was discussed in detail in lecture number 30. So, in AC equivalent circuit of a practical synchronous buck converter, that can be we have already obtained in the previous lecture, and we can obtain any output impedance, input impedance, audio susceptibility, control to output transfer function, and these are the summary of transfer function of a practical buck converter. This is the control to output transfer function. This is one of the most important that we are going to deal with. Audio susceptibility is also very important. Then output impedance is very important, and for all this transfer function the common denominator, which is the pole, is nothing but this transfer function. Okay? And this is a small signal block diagram for the open loop converter. Alright. Now, we want to first go for voltage mode control, because today discussion we want to talk about single loop control, and in subsequent lecture we will go for two loop control in current mode, but in single loop control we want to restrict our discussion of loop gain analysis for single loop voltage mode control. So, you know that if you take any DC-DC converter, here it is a buck, but it can take a boost converter, you can take flyback converter, you can take buck boost converter. If you take the output voltage, then this is a feedback voltage, and generally this feedback gain come from the resistive divider, and that we have discussed. Then it is compared to the reference voltage. In fact, reference voltage also there should be a gain, feedback gain, because you need to scale the reference voltage accordingly in order to match. That means our objective ultimately to obtain V0 equal to Vref at steady state desired voltage. So, if you step down by a factor of kf, then you have to make a scaling factor here, so that Vref to V0 can be mapped. Next, what is PWM modulator? Here we have a shortwave waveform and the control voltage, which is the output of the controller. This is our controller, right? Sometimes we also call compensator controller. So now this PWM block, actually this block is already there. So, this block is here. So, this PWM block is this, which is a trailing edge modulation. This is our trailing edge PWM block. Why? Because the switch turns on at the every rising edge of the clock, switching clock, it set the pulse. So, switch turns on, and switch turns off when the control voltage intersect with the shortwave waveform, that means when it intersect. Okay. Now, and it has a latch circuit to avoid this jittering behavior, comparator behavior. It should not be reflected in the output side. So, latch will make sure that once the switch turns off, it will not be turned on throughout the rest of the interval. So, now we are closing the feedback loop. We saw the output voltage has, if we draw the output voltage waveform, it has some amount of switching frequency ripple. In fact, in practical converter there should be some due to ESL effect, for boost converter anyway this direct jump will be there due to the ESR. So, when you sense the voltage, and if we use a high frequency I would say high frequency op amp, right. So, this switching ripple information will be passed to this loop. That means, the loop will say this switching frequency ripple information. But we will discuss today that our small signal is valid within a certain restricted bandwidth limit. That means, whatever we talked about the control bandwidth of a DC-DC converter using small signal based design, it is coming due to the model limit. Okay. So, wherever our actual transient response using small signal model, as long as it is matching with the switch simulation under closed loop, up to that point we can go for, we can increase the bandwidth. Beyond that, the model will start, there will be mismatch and our model is not valid. So, that means we need to slow down this process because our small signal model, and but before start discussing, we cannot afford to introduce this switching harmonics information or the switching ripple into the loop. And if you take the power spectrum of the output voltage, in fact it should be even smaller. So, it will have a very high component, the power, which corresponds to the DC component, because it is ultimately a DC-DC converter. Okay? But there will be some component in the switching frequency and harmonics. So, in order to avoid, that means we want to attenuate that the switching frequency component should not be injected into this compensator or the PWM. So, we need to put a low pass filter here. That means typically this is called, we call as a Nyquist frequency, F Nyquist, because it is generally half of the switching frequency. And our small signal model is not valid. In fact, our averaging technique is not valid beyond Fs by 2, which is a half of the switching frequency. And our small signal model even is not valid, we will show, is more than 1/10 of the switching frequency. Okay. So, we are talking about Nyquist frequency where our validity of the average model will come, the average model concept is not applicable beyond that. But we need to put a low pass filter to attenuate, because low pass filter it cannot immediately, so it should attenuate this effect. Okay. So, that means in order to attenuate, we need a pole either at Nyquist frequency or the lower frequency, that is needed, and we will see that we will have pole there. So, now the MATLAB implementation of voltage mode control, I think that we have discussed. So, this block we have already simulated, this is our buck converter, resistive load, and we are considering additional transient, load step transient, supply transient, load transient, then reference transient. Here using a constant current load, okay, load transient, and this is the block diagram. And if you go inside this block, that means if we go inside, this is our controller, then we will see that here is my transfer function, here is my, this is my error voltage, okay, and this is my sawtooth waveform, this is my ramp signal, and this data conversion block is used to avoid any incompatible data matching. So, that is why this conversion block is used to make this switching clock, because sometimes the signal can be double format and here it can be binary. So, in order to match such kind of binary double format, we can use simply a data conversion block, it will make sure they will be compatible. Now, this transfer function here, actually if you go, let us go to the MATLAB, I will show you that if you go to the MATLAB model, if you go inside, this transfer function is the one which you are calling from the MATLAB function, numerator control, denominator control. Okay. So, it is, that means this transfer function has numerator polynomial and divided by like a denominator polynomial. So, this will be used in the MATLAB numerator denominator coefficient, and this coefficient will be decided from the design process. How many type of such compensator? That means we are talking about this controller. What are the typical controller that we consider? One is type 1, which is a pure integrator. Though we should not use pure integrator, we can place a pole very close to imaginary axis. We can consider a simple resistance here to avoid sometimes saturation problem of the op-amp in a practical op-amp. Okay. So, type 1 compensator means it is an ideal one which is 1 by S, where this resistance will not be there like a mathematically. Type 2 compensator, where we are talking about, so here it is like a one pole at origin, here we are talking about one pole at origin plus there is one controller 0 divided by one controller pole. This is type 2, and the next one is the type 3. Okay, so type 3. In type 3 we have one pole at origin which is common and we have 2 0. So, that means it is the numerator coefficient which is a second order, and the denominator coefficient which is also second order, okay, second order, and another is a PID controller. So, in this particular lecture we are talking about PID controller, but we will eventually find the PID controllers are not sufficient because of the degree of freedom, less degree of freedom when you talk about shaping the closed loop bandwidth as well as phase margin. Okay. Then we will consider an additional pole, that means eventually we will go to type 3 compensator in the subsequent lecture. But in today's lecture we will talk about PID controller in order to match the model and validate the process of validation. Then the same approach you can use for the type 3 compensator to carry out the design under voltage mode control. Okay. And also it will show that PID controller is of course not sufficient for a boost converter because there is a right of plane 0. So, you need to anticipate that effect using a type 3 compensator. Okay. So, generally that is why the type 3 compensator is a very popular choice under voltage mode control. So, the small signal closed loop block diagram, if you draw this feedback block diagram. So, this GVD we have already discussed, the control to output transfer function, modulator gain, then controller transfer function, then this is audio susceptibility, output impedance, this is our feedback, that means sensor, and if you want to draw the loop gain analysis, then this is our loop, this is our single loop control loop transfer function, and you will find, as I said, that we need to map this Vref, we need to map to V0, that means we want to make them equal. So, if we set a gain kf here, then this h of s should be okay. First thing before we move forward, mapping. So, what is our closed loop transfer function? Our V0 to Vref, that means this V0 to Vref can be written as kf, this kf, h of s here multiplied by loop transfer function by 1 plus loop transfer function. And if the loop transfer function is very high, then it can be approximated by simply kf by hs. That means, if you set this also equal to kf, then your V0 will be approximately equal to Vref if the loop gain is very high loop gain. But this very high loop gain require two things. The bandwidth of the entire range, it will be very high bandwidth, and also the very high gain. So, that means it is not possible because our op amp loop gain is limited due to the finite gain bandwidth product of the op amp, and also to avoid saturation, because if you increase the loop gain, it may so happen their control voltage, because ultimately what happens, there is a PWM block, modulator block. What does it do? There is a sawtooth waveform, right. So, if you sawtooth waveform, so if you take the sawtooth waveform, now this is our control voltage, right. Now, if the modulator gain is very high, under transient this waveform can go above. So, it can be like this, and then the duty ratio can saturate, and under this condition, first of all, your small signal model is not valid, even for a large perturbation it is not valid. The secondly, see high DC gain, it will saturate the op amp, and we need to avoid, because that analysis with saturation will go into nonlinear analysis, and we want to avoid, and we want to restrict the whole loop gain analysis in terms of linear transfer function. So, that we want to limit within the saturation limit of the op amp. So, that means we cannot have very high loop gain. Now, requirement under finite loop gain, that we have understood. So, if the loop gain is finite, now what we need to ensure? The robustness against parameter variation and unmodeled dynamics, because the transfer function GVD here will consist of load resistance, input voltage. It is also that those are the operating condition. Then inductor value, capacitor value, there can be variation, tolerance of the components, and there are some unmodeled dynamics, because we have not incorporated the dynamics of the actual switch, the dynamics of the ESL. So, there will be some unbottleneck, although they are very high frequency, but that also can be incorporated. Then we should have acceptable stability margin, gain margin, phase margin, and we need to achieve desired adequate transient performance, because we should not have very high overshoot undershoot, but our settling time should also be very fast, and we should also provide some useful design guideline. So, in the subsequent lecture we will give you all the guidelines, design guideline. Okay. So, the loop gain analysis of a buck converter, as I said that we need to map between V0 to Vref, right. So, if you set a Kf gain here, then we should set the gain of the resistive divider to be Kf, and the frequency, if we put a unity gain buffer, the bandwidth of the op amp is very high. So, you can ignore that transfer function. So, the loop transfer function will look, that means since there is, this will be replaced by Kf. So, we have a Kf here, we have Kf here. So, you can remove this and this will be a loop transfer function. Okay. So, this is a loop transfer function. It consists of the open loop pole, open loop transfer function, control to output transfer function. Loop transfer function. So, we have a ESR 0 here, and if we take as a low ESR, it will be at high frequency. We have double pole, generally they are complex conjugate. If the load resistance is high, so it will lead to poor phase margin. Then we have if we have a high DC gain, if we want, that means we want to shift up the gain plot, then the bandwidth can be increased, but it will lead to poor phase margin. And since the DC gain dependent on the input voltage, that is a drawback of the voltage mode control. And if we apply input voltage feed forward, which we discussed in week I think week 3, that feed forward technique, and if we use the input voltage feed forward, then we can make the loop gain independent of input voltage, and then we can accordingly design the loop gain. But if the loop gain is high, it will lead to poor phase margin. So, we need to anticipate by suitable compensation. Modulator gain, which is 1 by Vm. So, if you take a lower voltage, that means I am talking about this peak to peak voltage. So, this is my Vm, this is 0, and the modulator gain is 1 by Vm. So, if the Vm is small, modulator gain is large. In the modulator gain is large, then it will shift up the DC gain of the loop. So, it can increase the bandwidth, but at the cost of poor phase margin. Okay. Now, we are talking about a PID controller, an ideal buck converter. So, if we take an ideal buck converter, then the transfer function becomes simple, very simple, and this Vm 1 by Vm is nothing but our Fm. Okay. Now, ideal PID controller like this, but it is physically not realizable, because this derivative action, pure derivative cannot be realized, because even if you use an op amp has a finite bandwidth. So, naturally it will give rise to a band limited derivative action, and we will discuss. Now, if you want to compensate this, then what we should do? The controller transfer function written like this, it can be written. We need to cancel using this. Suppose we are going for stable pole 0 cancellation, and we want to cancel this. That means, we want to cancel these two terms. And if you do that cancellation, then the polynomial from here you can find that Kp by Ki, which is this term, will be equal to this term, right. It is L by R. Similarly, Kd by Ki will be equal to Lc. But now, we have two equations here, equation 1, equation 2, but we have 3 unknown, Kp, Ki, Kd. So, how to solve? Now, once you set this compensation, our loop gain, because we are cancelling this pole with the controller 0, we are cancelling, then the compensator will have, if you go back, what was our compensator structure? It was Ki into the controller numerator divided by S. So, this term is getting cancelled with this term. So, we will end up with Ki V in Vm, this is a term. And if you draw the frequency response, that means S equal to j omega, then this will be the transfer function. And if we plot the frequency response that we get like a Bode plot, then this will be minus 20 dB per decade, minus 20 dB per decade, and this point is called, we call it as a gain crossover frequency. And this will be actually the closed loop bandwidth, the gain crossover frequency. Okay. And since it is a fast order, only single pole, so this will lead to 90-degree phase margin, because it is a fast order system. So the closed loop will also be a fast order system. Okay. So that means the frequency response I can select, that means if I at gain crossover frequency, that means at gain crossover frequency our k j omega, if I take amplitude at gain crossover frequency, it is unity. And if we can compute from here, that means our V in by Vm into Ki by omega c is equal to 1, and from here we are getting integral value. Okay. So you can set it, and other parameters also we have. Now we have another equation, equation 2, equation 3. So you have 3 equation, 3 unknown, we can solve it. Ki. So now Ki by, if we want to increase the gain crossover frequency, then we need to increase the integral gain, simply the integral gain. But ideal PID controller is not physically realizable. And of course, we started with an ideal buck converter. Ideal buck converter also does not exist. So now we are talking about the practical PID controller. In a practical PID controller, we generally use a derivative filter, and it is the derivative filter, and this comes either you can put an intentional derivative filter, or it can be the part of the op amp, because op amp has also band limited, its bandwidth is limited. But we generally, because we take a op amp with a very high bandwidth, so we place this derivative pole as filter pole as per our wish, because we need to choose this pole in order to meet certain requirement. So that is why it is our design that where are you going to place this derivative filter pole. So the structure of this PID controller, if we take generic structure, so this controller I can say again the numerator of the controller, which is nothing but it is derived from here, and this is our denominator of the controller. So this is my controller denominator. So we can find out what is K1, K2 in terms of Kp, Ki, Kd, and there is now tau d term. Now again we are talking about a practical PID controller which is physically realizable, and a practical buck converter which is a actual experimental setup or actual implementation. So in the loop gain, our first objective, that means we are again go for stable pole zero cancellation. If this is our controller polynomial, numerator polynomial, and this is our planned denominator polynomial. So first thing we want to do, the controller numerator polynomial is set to the planned denominator polynomial. Okay, that means they cancel. And if you do that, then K1 here will be equal to 1 by this, K2 here will be equal to 1 by omega 0. And we also want to set that tau d should be, it should cancel the ESR 0, this ESR 0. So this controller pole is used to cancel this ESR 0. That means here what is ESR 0? It is 1 by RC into C. So it is simply RC into C, that is here. So here we have how many equation? 1, 2, 3, but how many unknown? The PID controller we unknown are Kp, Ki, Kd 3 plus 1 derivative time constant. V in Fm alpha Ki by S, and if you substitute S equal to j omega, then so because our what was our K of S? K loop of S, it was V in Fm alpha 1 by S. So we replace S equal to 1 j omega. Okay. Oh, there is also Ki. Now, same at gain crossover frequency, it is 1. So, from here we can set Ki equal to this value, and again the loop transfer function will be a first order, just like a pure integrator. It will have minus 20 dB per decade, okay, and phase margin is 90 degree. So, if we select the gain crossover frequency, then you can find out Ki by using this formula. We can find out Ki by using this formula, and then we need to check for model validity. Okay. So, in order to check the model validity, let us go to MATLAB, because we want to check using MATLAB transient simulation. So, now since we have already discussed in lecture number 30 the step by step all procedure, how to this is our MATLAB script file. Okay. So, I am just trying to just summarize this. We are not going each and every line. So, these things are already discussed in that lecture number 13, and these all are equivalent, etc. is explained. But now here we do not need a practical duty ratio. Why? Because in the earlier case we need to have a practical voltage, because it was open loop. So, in order to, because we obtain the AC simulation transient simulation from small signal, and we wanted to add that AC small signal response with the steady state operating point, DC operating point. For that, this was our operating voltage. So, this was our operating voltage, right. So, in open loop you need to find this operating voltage, which depends on the load current, duty ratio and other thing, right. So, that is why we derive. But here we are doing closed loop control and we have an integrator. So, we can assume that our operating point V0 operating point is nothing but Vref, where we are setting, because we are using an integral gain, and you can assume that average will come to Vref within reasonable amount of time, though they are defined in terms of limit t tends to infinity, but we will get close to the same value within a certain finite time. And these things I already explained, duty ratio, open loop, and load resistance we set 0.1 ohm, then R equivalent we can obtain alpha. Now, the modulator gain, Vm we took 10, 1 by Vm is a modulator gain, and this is the implementation we did it. This is a closed loop. Now, this is our transfer function, this is our controller, and this is our Vcon, and this is our ramp voltage. So, this all we have discussed. Now, you want to double pole all these parameters we have already explained earlier, the characteristic impedance, ideal, practical, natural frequency, then the Q factor. We have also defined earlier the poles and zeros. So, delta P is my open loop pole. What is that? Delta P we have discussed, and this is we have plugged in into MATLAB, and ESR 0, then another pole omega L, this will be needed for output impedance. ESR 0, the other poles also we have written. So, this thing we have repeated in lecture number 30. We have defined the open loop control to output transfer function like this also we have discussed in that lecture number 30. Open loop output impedance also we have discussed lecture number 30, how to write with transfer function. So, these are all explained, the denominator pole is common delta, and it has 2 0, one due to ESR and another due to the DCR equivalent resistance of the inductor and RDS on. So, here omega L, what is omega L? Omega L is nothing but R equivalent by L. Okay. Then audio susceptibility we have also discussed, open loop audio susceptibility. Now, we are going for closed loop. So, from this point we are now adding new thing. So, first we want to design a PID controller, and we have discussed in the PID controller what was, if you go back to our PID controller, what was our Ki. I mean, if you go back, yeah, our Ki is omega c alpha by Fm Vin. Okay. So, that means here if we go to PID controller, what is our Ki? Ki is omega c alpha by V in Fm. Okay. So, now if you check, initially it will ask for your crossover frequency. What crossover frequency you are going to set? It is user choice. So, it will ask for the input, and I will show you in the actual MATLAB. Then this frequency I will ask in kilohertz. Okay. So, it has to convert into radian per second. So, it is 2 pi fc into 1/3, because we are asking in kilohertz. So, you have to convert into radian. Okay. Then Ki, this equation we are plugging from here. Okay. And the numerator coefficient is nothing but of the controller numerator is what? So, this is the controller numerator, n of c is equal to what? It is our delta of s, that is the denominator of the plant, which is a delta p. Okay. So, your overall controller numerator is Ki multiplied by, that means delta s. So, this is exactly what is here. Okay. What is denominator? Denominator, we want to take this controller, that means there is one pole, right? There are two poles, one pole at origin, another pole will be s by 1 by tau d, like this, right? This is our pole. So, the tau d is ESR 0, because we want to cancel, that means we are taking 1 by tau d to cancel ESR 0. So, here tau d is nothing but 1 by ESR 0. So, this is exactly here, and then the controller transfer function. Next, what is the loop transfer function? It is the transfer function of the control to output transfer function, which include the modulator gain into the controller, right? Then what is our closed loop output impedance? So, if you go back to our plant model, so suppose this is our GVC and this is our GC, okay, and this is our open loop output impedance, okay, and this is our V0. The V perturbation 0 minus, and this is my loop transfer function, K loop. That means my closed loop output impedance will be open loop output impedance divided by 1 plus loop transfer function. Similarly, closed loop transfer function will be loop transfer function by 1 plus loop transfer function. You can show from here. And closed loop audio susceptibility, because we have not incorporated, so here we will have another component, audio susceptibility, that can be shown as open loop audio susceptibility divided by 1 plus loop transfer function. So, this all thing we have written here. Then we can do frequency response plot, Bode plot here, and we can use this, we can obtain gain margin, phase margin, gain crossover frequency, phase crossover frequency using this margin, because we want to show, if we want to plug in, we want to see actually Bode plot whether we are getting minus 90 degree phase margin or whatever gain crossover frequency. So, this is our loop transfer function. This is the compensated loop transfer function. Here we have used, what is our desired. So, you see this is our cutoff frequency. So, I set here cutoff frequency to be 1 kilohertz, whereas my switching frequency 500 kilohertz. It is too low, but I will show you why. In a moment we will go to that point, 1 kilohertz. So, 1 kilohertz, and you see the phase margin, phase is minus 90 degree. So, our phase margin is, in this case, is 90 degree here, right. So, from the Bode plot it is very clear, and you can see it has like a minus 20 dB per decade. Okay. Then closed loop load transient response. We want to see the load transient response under closed loop. So, again I have explained, this is a total simulation time, this is a T step. Okay. Okay. So, I want to show you how does it look like. So, this is our, okay, response. Now, I am applying a load step transient here. So, this time this is my T start, this is my T start, the starting value where the actual step is applied, and this time is my T sim, is the total simulation time. So, here we have applied a load step transient, and we know here I am applying the 10 ampere load step, no step for the input voltage and the reference voltage. So, I want to measure the load transient response by closed loop output impedance. That means, it is minus load step size and step response of the closed loop output impedance, which is the inverse Laplace. So, this is the step response of the closed loop output impedance, and the AC response will be minus delta I 0, that means minus delta I 0 into my Y of S, where Y of S is my AC response. What is my Y of S? So, it is my step response of my ZOC. So, it is a unit step response. Okay. Now, so here it can display the phase gain crossover frequency in terms of kilohertz, phase crossover, phase margin. So, it can show the Bode plot of the loop gain margin. So, I will show exact switch simulation we want to match. Okay. And how to do exact switch simulation? So, since we have already computed the controller, I have shown you that this is the controller we have computed, the PID controller. So, this controller will be this numerator coefficient, the denominator coefficient will be plugged in to actual switch simulation, right. So, here if we go inside that controller, inside that there will be a controller where we are using coefficient numerator control, denominator control. We will go to that very soon. It is actual switch simulation. Then I will use a plot command, I will show you what is this, and then figure this is my AC simulation response, transient response of the small signal model, and I am adding the operating point, which is a reference voltage. Since it is closed loop, so the operating point is Vref. Okay? And then I am also adding the time offset, which is a T step, because otherwise the original simulation will be from 0 to the time we are actually extending, but we are adding the offset time. And this is my the plot .m file, which will plot inductor current and the output voltage of the actual switch simulation. So, now we want to check verify step reference transient using voltage mode control with PID controller, verify step load transient, verify supply transient, and we need to observe. So, let us go back to our MATLAB simulation. So, the first thing we want to check is the step reference transient we have set. Okay. Now, here it will ask for bandwidth. Let us say we are just setting, let us say 500 kilohertz switching frequency. So, we want to set 110, that means 50 kilohertz is my gain crossover frequency. Sorry. So, again if I actually 50 kilohertz is the gain crossover. So, here our gain crossover frequency is pretty high, and we need to check whether our response actually matches or not. So, this we are setting yes. So, this is our gain crossover frequency for 50 kilohertz. You see the response is matching to some extent up to certain, maybe it up to, because we are trying to achieve fast order system, because you see the loop transfer function is simply gain by integrator, it is minus 20 dB per decade. So, the closed loop system should be a fast order system, but you see actual closed loop does not actually switch system does not behave like a fast order, because there is some kind of oscillatory behavior which is not actually matching. So, that means they are matching to some extent up to some initial stage, after that the model diverges. Okay? That means if the model does not match, so we cannot predict, whatever we predict from small signal model, it will simply not work, because your actual switch model is deviating. What is the reason? If we reduce the bandwidth, we run again, we reduce the bandwidth to let us say 10 kilohertz. Now, we have reduced, earlier it was 50 kilohertz, now we reduced 10 kilohertz, whereas the 500 kilohertz is our switching frequency. you see when you reduce the 10 kilohertz, the response again becomes slightly different. So, initially it was matching the initial response, now the problem start even in between. Okay? So, that means the response is clearly showing it is not perfectly matching. Okay? So, that means this, okay, now you further reduce. Okay? So, if you further reduce to let us say 1 kilohertz is very low, too low, then I want to match the switch simulation. So, it is 1 kilohertz 1 by 500 times slower. It is very much slow, and if you see the response here, they are matching quite nicely except for the initial stage. That means the converter is actually behaving like a first order except for the very initial stage, there is a slight deviation. That means although we are trying to achieve first order, but actual voltage mode control, it is very hard to get first order response, at least for this simulation. Now, so that means there is a model limit, that means the model limit when you go for closed loop performance, particularly for reference voltage transient. So, in order to get some desirable response, we need to limit the bandwidth is 1 by 500 times, which is very slow. Okay? But if we go to load transient response, that means we are talking about load transient response. So, in the load transient response, now we are applying a load step of 10 ampere for example, and no supply voltage transient, and now since we are applying load transient, this should be ZOC, closed loop output impedance, that we have discussed, and this should be multiplied by delta V0 with a minus sign, because we have discussed this. Now, again let us start with 50 kilohertz in this case load transient response. For load transient, we want to see whether the model matches or not. This is with for load transient. So, you see in this case the model is matching reasonably well for load transient response. There is slight deviation, but still it can capture the transient performance when the load transient is constant. That means this model is valid close to, that means if you go, this is for 50 kilohertz crossover frequency, where 500 kilohertz is the switching frequency. Now, if you go to let us say 100 kilohertz, that means 1/5 100 kilohertz, then what is our response? Is it going to match or not? So, we are going to see the response, and you will find now the response is diverging. I mean their actual peaks is down, so the response start diverging. Okay, so that means we should not use 1/5 of the switching frequency as the bandwidth, because the small signal model is not accurately matching. Okay, they are not valid. If we further reduce to 1/10, let us say we are making 1/10, so it is 150, that means 10 kilohertz, then we want to see how far they are matching for the load transient performance. So, in this case you will find they are matching quite accurately, not accurately, because there is still some deviation. So, that means as we push and push higher and higher gain, but I can say the model matching using first order approximation is not the right solution. Once you go for type 3 compensator, you will get perfect matching even 1/10 of the switching frequency. So, here because we want to achieve first order response, that is why it is not matching correctly. Okay? And here delta V in, our load transient is 0, it is multiplied and we need to use G. So, this one. Okay, so let us see what happens. So, here let us say we are setting 110 and we are trying to match the model, and see this is for supply transient, whether the model match or not. So, even for supply transient it is not matching accurately, because the model start diverging, because as I said, the model has to be, if we go for very low like 1 kilohertz, and then let us check that how far the model matches. So, there is still some deviation. আচ্ছা সৌরভ এই পার্টটা না কেটে দেবে একটু, হ্যাঁ এই সাপ্লাইটা, ওকে। So, the supply transient also similarly we can carry out supply transient response. Okay, so observation is that the first order model is not accurate for cutoff frequency roughly around FSW by 10, and we are familiar with this, that means 1/10 of the switching. So, first order model is not matching. So, this may not be a good way to design. That means, this model, if you use this model, we have to limit our crossover frequency to 1/100 of the switching frequency, and actually nobody will buy this power supply. So, the model limit for overdamped PID, for both ideal and practical PID controller, the loop transfer function reservoir and ideal integrator. First order closed loop system expected to be overdamped, but actual loop is not matching, it is validity is in question, there is a significant deviation. So, we should not use a PID controller for analog voltage mode control, because we do not want the first order response, we want an additional degree of freedom. So, the extra pole has to be added with the PID controller, and that will lead to a type 3 compensator, and using which we can get more accurate model, very accurate model up to 1/10 of the switching frequency. And there we can, because here our objective in overdamp is 90° phase margin, we do not need that. Even if we achieve close to 60° phase margin, it is 60°, it is good enough. But if you add another pole, I will show you, for a buck converter, you will have independently, you can set crossover frequency and phase margin, you can set independently. So, that will be discussed in the future class. So, in summary, we have constructed the loop gain, we understood the design requirement, we have analyzed a PID controller design in a buck converter, then we have discussed step to verify the closed loop small signal model using MATLAB transient simulation, and we identified the model limit based on small signal design. And in the next lecture, we will talk about type 3 compensator, where we can go even higher up to 1/10 of the switching frequency with reasonably good matching. So, that means we understood how to match the response of a system of the actual switching converter using small signal model, and we will discuss the design procedure along with the validation of model in the subsequent lecture for voltage mode control, for buck and boost, as well as current mode control. So, with this I want to finish it here. Thank you very much.